Last time we saw the linear combination of s orbitals. Now we're going to see the linear combination of p orbitals. This shows the normal dumbbell shape of the p orbital, and when you learn about the wave functions, the mathematical functions, show you that one lobe has a positive mathematical sign and one lobe has a negative mathematical sign. And again, it's got nothing to do with electron charge or proton charge. This is just a mathematical sign of the function. So when we put together these two p orbitals, we have to do the positive, we have to do the addition, but we also have to do the subtraction. And remember, subtracting is the same thing as adding the negative. So the picture in red shows one combination, the picture in black shows the opposite combination. I chose to show it as an addition, but when I add the negative, so that's why the p orbital on the right changed its signs on the lobes. We push together these two atoms to get the nuclei closer together. Negative overlaps negative. That's going to make constructive interference, where we get more negative in the middle, and then the lobe on the outside will still have a positive sign, and the same thing is true for the p orbital that started on the left. This part of the p orbital stays positive even when we push those two nuclei closer together. The subtracting case, now we're going to take negative with positive, so we get destructive interference right in the middle, and just like with the s orbitals, we're creating a node where that happens. A small amount of this lobe is still present. It's negative in sign, and then we still have the positive lobe. And on the other p orbital, part of it gets destructively interfered with this negative, but then we still have a little positive lobe, and then on the outside negative. Every time we do this combination, one part is going to give us a bonding MO, and the other possibility gives us an anti-bonding. The one at the top is good for bonding. The one at the bottom is bad for bonding because we created the node. Notice that the part that's good for bonding shows that the electrons can exist between those two nuclei along that internuclear axis. So this would be called a bonding MO that came from a p orbital. The one at the bottom is anti-bonding, and it came from a p orbital, but it's also along that internuclear axis. We can see the other possibility if the p orbitals are oriented this way. This time, positive overlaps positive. We get constructive interference above. Negative overlaps negative. That's constructive interference below the internuclear axis. When we do the subtraction, positive overlaps negative. That's going to give us destructive interference. So again, we create a node, and we end up with parts of the p orbital that aren't completely overlapping, still having a little bit of the p orbital left, but notice the node makes this bad for bonding. There's no node that we created for the top picture, so that's good for bonding. But also notice that this is above and below the plane, so this would be a pi molecular orbital that came from mixing p orbitals. So this would be a pi, a bonding p molecular orbital, and the picture at the bottom is an anti-bonding, a pi star molecular orbital.